Indeed, thank you. Yes, I'd like to begin actually by thanking the organisers for having organised such a wonderful, fun week here at the IAS, so thanks for that. And thanks indeed to the organisers for giving me the opportunity, the unique opportunity to be the final speaker. So given that, I thought I would actually sort of blend in not only our own thinking and work, but sort of pulling in things we've heard in the last few days. So really what I'm going to do is have really 5 key ideas in this talk. They're going to be labelled thus, with this font and colour, and I'm going to invert my triangle, meaning I'll begin with each key idea's bottom line and then elaborate over a few slides. Okay? So the key idea bottom line will come at the beginning of each of the 5 and then a few slides thereafter. And there's 5 of them, and they're numbered so you don't have to count. Right. So the first idea we heard actually from Jerry a couple of days ago. The idea really, could you have, what comes first, the supermassive black hole or the nuclear stellar cluster, right? So we look in the center of our galaxy, we've clearly got both. And I'm going to explore a little bit that idea a bit more now, and a few of the consequences which maybe aren't completely obvious. For example, actually, if you have a stellar cluster with a black hole, and I magically dial down the supermassive black hole mass, actually it turns out that the collision rates go up if I keep the same orbits, the same orbital elements. So magically somehow do that, the same A's and E's of the stars, but lowering the mass of the supermassive black hole, we'll see in a minute that the collision rates go up. So you can have much higher collision rates in the past. And it's an interesting question, right, anyway, to ask what comes first, the chicken or the egg. And we saw some of this already earlier in the week. M33 is an example of this. So M33, if you look in the middle, there's a nice nuclear stellar cluster, but no black hole, or at least precisely an upper limit that's really quite low mass. And I took this plot actually from this review by Neumeier and Welcher in 2012. It's actually quite a nice review. It's in a journal whose name I've forgotten, but it's an unusual journal. So I think I'm not sure even if it's on ADS, but you can find the archive version on ADS. So I recommend this to you, and this plot is taken from it. And you can really see the sort of dichotomy then of nuclear stellar clusters, right? Because there's velocity dispersion on a log scale here, and then the black hole mass here on a log scale again, 10 to the 4, 10 to the 6. And all I want to take from this is really there's 2 groups of objects here. There's a group of objects here with velocity dispersions 20, 30, 40 kilometers a second. Then there's a gap, right? Here's the Milky Way and all the other stuff up here with velocities 100 or 200. And there really seems to be a gap. And these are the ones with upper limits. So we could imagine that these don't have a supermassive black hole. They're sort of beefy globular clusters. I'm going to use beefy one more time at the end of the talk. When you hear beefy again, we're done. But by beefy, actually that's no good, is it? Repeat it again one more time. What I mean by that is a globular cluster that's a bit more massive. So these nuclear stellar clusters here are somewhat more massive, slightly more massive. But think of them rather like globular clusters. And all the stuff you've ever heard me talk about globular clusters before, about X-ray binaries, Pouillet's work and all that lot, will apply to these guys before whatever magic happens to them to make them these guys. That's the point. Okay. Right, so I could, pardon me? The source, I don't know, right? Well, we'll see in a minute. Well, we have some ideas, and we'll get onto them in a second. Above a number around here, certain things happen, or certain things fail to happen, which is actually on my next slide. So. Okay, that's good to know. So that's from anal Seth, yeah, good. But I'm going to talk a little bit anyway about what we think happens above this limit, because there is something going on that stops these objects. If I take one of these objects and make them more massive, at some point here a number of things will happen. There'll be a failure of globular clusterness. This is a busy slide. I'm not going to go through all this. You can watch it later on YouTube. But the key point here is the following. If I have a globular cluster and I have binaries in my globular cluster, binary single scattering can heat the globular cluster, right? Because binaries get a bit tighter, the third star gets some energy, and that inserts kinetic energy into my object, so it can help support my globular cluster against core collapse. Now let's imagine my binaries are rather prosaic, rather boring, regular stars. So a lot of them are non-compact stars, they're main sequence stars. If I get above a velocity dispersion about 40 kilometers a second, this is work I did, I should say, with Cole Miller, above 40 kilometers a second, the binaries that are hard enough are smaller, right? So if I'm a wide binary, my 2 hands are a wide binary, and this gentleman is a third star, he encounters me, he dismembers me, right? Okay, so my binary gets broken up. So a hard binary has to be smaller at higher velocity dispersions. And at about 40 kilometers a second, the hard-soft boundary is some few 10, 20 solar radii for solar-like stars. What this means is during the binary single encounters, I'm going to have mergers. I can't heat, because if I have a collision between 2 of the stars, during those sorts of encounters, I'll merge, make a blue straggler. The point is I don't kick out a third star at high speed. So the binaries will fail to heat the clusters once the binaries are so small such that during binary single encounters, mergers take place. You can play that back several times later, but it makes sense. Right, so that's what's going on, and that could be, modulo the comment about new observations, at least what's beginning to kick in over here somewhere, right? So it'd be interesting to see these intermediate systems. Right. The other point as well is that, so if you can't support yourself, if you're in that regime above 40-some kilometers a second, and you get to a regime, if you get to a regime by core collapse, so you fail to support yourself and you get very high densities, then this is a good prospect for the sorts of things we heard about with the tidal disruptions, right? Or other things can happen. I should also mention, to advertise another work I did with Cole Miller and Gillian Bellaveri, which was sort of the opposite problem. It was not avoiding making a black hole, but trying to make a black hole super early in the universe. If I take a nuclear stellar cluster like M33 and pour in lots of mass, so to sort of significantly change the total mass, I can shrink the cluster, and I can get runaway mergers in there. I think you mentioned it actually in your talk, didn't you? And people can read that for more details, but this can potentially help make a seed black hole at high redshift for the very high redshift quasars we see. So this is another point to think about. This is a wet with gas or dry growth of nuclear stellar clusters. So how are you building these things up? Are you pouring gas into the middle of a galaxy, or are you pouring clusters of stars? And that's different, right? And probably, annoyingly, really, both are happening, I suspect, right? Okay. So now we have this. We have two kinds of stellar clusters. We have the globular clusters, not to be confused with the galactic center, where there's no black hole, no supermassive black hole. So I'm going to talk about those as GC-like objects. And if I have a supermassive black hole in my cluster, I'm going to call that an O dot. You can, if you don't know why it's called an O dot, you can ask a friend later. They use LaTeX. Okay. Right. So I mentioned earlier about turning down this black hole mass and how the collision rate goes up. And I want to spend a few moments to explain that because it's not completely obvious to everyone maybe. So this is the gravitational cross-section to have two stars, M1, M2, pass within a distance r-min. And Simon is not in the audience, actually, because he wanted me to do this. So the point is, for everyone, and Simon out there in YouTube land, is if I have a low enough velocity, rather than just fly by, the stars feel their mutual gravity and they deflect inwards. It's called gravitational focusing, and it depends on what the V infinity is. You can imagine at very high speeds they zip past, at low speeds they get focused. And that term, you can solve energy and angular momentum conservation and get this term, that's the gravitational focusing term. And you can see for globular clusters and solar-like stars, GM over R is a V squared, right? So GM solar over R solar is about, 430-some kilometers a second, which is a hell of a lot bigger than 10 kilometers a second. So in globular clusters, in my GC regime, we're super focused. And that has effects on cross-sections, as we'll see in a little while. But it also has a complicated effect on how the rates go. So the rates are an n sigma v, dimensionally, right? So n is the number density of stars. Sigma here is not the velocity dispersion. Sigma is not the velocity dispersion. It's my cross-section here. V is what you really call a velocity dispersion. But then if you're in the regime of globular clusters, if you think of this, this will dominate. So my cross-section goes as 1 over v squared times a v. So the actual rate goes as 1 over v. The slower I'm going, the more often I hit things. And that's what we see here. This is log of rate in some arbitrary units, but the units don't matter here. And the rate is going down with increasing v. Okay, so here I have v infinity on a log scale. So globular cluster regime is here, right? Now if I go on the other side now, I go to the Stonka-Rooney big AGN kind of extreme, not in the middle center of our galaxy yet, but ones where you have a very, very massive black hole, it's 10 to the 8, 10 to the 9 solar mass black hole, and I'm still pretty close, then what happens is this number is tiny, this number is huge, the V infinity is huge. I'm superly not focused at all. So my stars are zipping around at 1,000 kilometers a second or something. And then what happens is what you'd expect. The cross-section is r squared, no dependence on V, and the rate has a dependence on V here, what we'd expect. The faster I'm traveling, the more quickly I hit people as I plow into the crowd. And that's what we're seeing here. Right? So to paraphrase slightly badly, what goes down must come up. Right? Somewhere in between there's a minimum, because it's a continuous function. So class, where do we think the minimum is? Well, the interesting conspiracy is the following. If you work entirely in solar units, which I do encourage you to do, you can actually work out speeds and things at 0.1 parsecs by putting 0.1 parsecs and the mass of the black hole in solar units. And this actually turns out to be this, right? Because it's 4 million and 4 million. Okay? This is the minimum. Right? So what does this mean? If I could magically take our nuclear stellar cluster somehow and dial back, but keeping the orbits the same. So not the speeds, but the orbits, right? So the number density of stars the same, but dial down the mass of the supermassive black hole, starting from where we are today going backwards, I have a much more collisionable system, where by collisions I mean things that hit. Apologies if you don't mean that. I'm not just about dynamical collisions. I mean physical collisions of stars will have happened a lot more in the past before you make the supermassive black hole. Okay. Absolutely. We'll come to that in a minute. That's absolutely true. So we're in the GC regime here, the globular cluster regime, and we'll come to exactly that point in a second. Right. In fact, we're going to do now. Speed matters. What's happening in my cluster depends not only on the number density, but the V infinity. That's the speed I'm talking about here. So if I'm actually in a globular cluster regime, I can have binary single encounters. I can exchange into things. I can have tidal captures, right? Make X-ray binaries. In fact, I'll just leap onto the slide that shows that. This is a plot of the number of bright X-ray objects versus a reasonable guess at a collision or encounter rate. So the numbers here just show you that these are globular clusters. This is Pouillet's work. You see that the higher encounter rate in a globular cluster, these are various globular clusters, this correlates nicely with the number of bright X-ray sources you get, right? So things are happening in globulars that mean a neutron star or perhaps a stellar mass black hole comes along, either tidally captures a star or exchanges into a binary. Two main sequence stars. The remote thing is a black hole, exchanges in, and you make a black hole X-ray binary or neutron star, low mass X-ray binary. And you see a lot more of these per unit mass in globulars than in the field. This all makes sense. But you can see the challenge here because, as I mentioned already, this hard-soft boundary, if everything is solar, just for simplicity here, the hard-soft boundary is something like a few AU, 5 or 6 AU, if the V infinity is around 10 kilometers a second, and the scaling is given here, -2. So in a globular cluster regime, the hard-soft boundary is about 1,000 solar radii. There's quite a lot of space to have main sequence binaries. They have room to have an exchange encounter without the sorts of mergers I mentioned already, at least sometimes. But if I dial up, if I mass up my supermassive black hole and my V infinities are more like 100, then 100 squared here, there's the factor of 100 there, confusingly, so 10 to the -2, then it's like 1/100th, right? It's much smaller. It's like 10 or 20, 10 solar radii. And we heard about that from various speakers, you know all you are, right? Looking at what happens, the interesting question, right? What happens to the binaries in the center of the galaxy? It's a very interesting question. But what happens is a lot of them will merge. As soon as they encounter things, they're going to merge because they're so tight. Okay. Or if they're much wider, they're just going to get ionized, which is a horrible phrase, not attributable to me, but I mean they just break up the binaries. And that's what people nicely showed us in their cool work earlier this week. Okay. Whoops. I should mention, this is a wholly aside I added, but it was a very important points that were made this week. There's ways of increasing eccentricity in your clusters, especially in the O dots, in the clusters where you have a black hole or some extra structure. A slightly massive flat thing, the young disk of stars, can also do things to you, right? And we had Kozai and Lidov, or Lidov and Kozai, or Kozai, depending on your inclination. That was sort of a joke. Okay. And resonant relaxation. The point is there's other things that can change the eccentricity, both what I call the inner eccentricity, meaning I've got a binary here. Here's, say, the black hole. I have the eccentricity of the binary itself. That can change by Kozai interactions, for example. That was very important. You can get things merging, changing the nature of them. But also, there's a very important point, is that the actual orbit of the binary itself inside this thing can change for various reasons, right? And you can get, for example, if I don't, well, even if I don't have a binary, imagine my binary is now a single object. Okay, now this is one of my red giants, which maybe I want to get rid of, maybe not. But if I make it more eccentric, at least sometimes I make it really eccentric, I might, for example, lead to tidal disruption around the supermassive black hole. Okay, so this is happening all the time, and these sorts of processes, particularly things that you get because of unusual things, because of an extra massive thing in the middle, or even just a flattening. Cristobal, is he here still? And Fabio? Oh, yeah, sorry, I can't see, so I'm semi-blind, apologies. But they've done some very nice work talking about the effects you talked about, like the shape of the nuclear stellar clusters, for example, right? So things like that here are very, very important. We should remember that. Okay, let me talk a little bit about red giants. And people have heard me talk so many times about red giants, and it's a story of failure that ends in success because our failure becomes successful, right? Over the years, as Ryan and others know, we've failed to get rid of these damn things, but now maybe we don't have to get rid of so many. Ryan made my job 7 times easier yesterday, which is great. But let me explain a little bit about why it is difficult and why it's not difficult. So I think it was actually, in fairness, it was Reinhard Genzel, I believe, who first pointed out, long time ago, in the 80s, right, that actually the timescale for a red giant to hit something in the galactic center is kind of comparable to a red giant lifetime. This is true, right? death, taxes, and end sigma v, the three inescapable truths, right? Okay, if you've got a reasonable handle of the number densities, the red giants will get hit. This is not the question. But the trouble is a number of things, because we're in the O dot regime in our galaxy center, right? We've got a massive black hole, things are zipping around at 100 or 200 kilometers a second. That's a big thing now for us in what happens to red giants when they get hit. This is different in the globular cluster regime. So the first sort of rule of thumb is the following. The stopping power is roughly the escape speed of a ball of gas. What do I mean? I mean, I've got a ball of gas, okay, self-gravitating ball of gas with a surface escape speed, and I hit it with a point mass of roughly the same mass. People have done that, we've done that, others have done that. It's computer simulations. The delta V, if you like, is roughly given by that number. That's a good sort of sense of the size of it, okay? So you can see a problem now. If I hit a red giant in a globular cluster with a V infinity of 10 or 20, surface escape speed of a giant going up the giant branch might be 50, 60, 70. So I can capture my object coming in, I get a common envelope, I get rid of the red giant envelope probably, and I make some kind of compact binary. It's a good way of making neutron star white dwarf binaries in globulars, for example, as many people have talked about. But I can't do that in the center of the galaxy because I'm hitting an object with an escape speed of 60 with a V infinity of 200 or something. So what happens is what you see on this movie. So here's a red giant, this is density, here's the thing hitting it, it's a nice bow shock, and this is the thing that's hit it a little bit later. It's passed through the red giant, but picked up some mass. I want you all to remember that it passed through the red giant and picked up some mass. That will be relevant in a few minutes. But in general, I don't get rid of the red giant this way. I can make a nice movie. If I had a typical collision, this is not a typical collision, it would look the same, but what would happen here, a 2 solar mass red giant would typically lose about 1 solar mass of envelope when it's hit by a white dwarf or a low mass main sequence star. It would make a good movie, but it wouldn't get rid of the red giant because 1 equals 2. Meaning, you all knew this. If you think of an HR diagram, the trajectory, the path of a 1 and a 2 solar mass star in an HR diagram as they go up the giant branch are rather similar. In brief, technically it's because what shines, what drives the shining, the energy in a giant going up the first giant branch is nuclear burning on a surface of the core, right? And the core of the 2 stars are rather similar. You know, you're standing on the surface of the helium core, you don't know if it's 1 solar mass above you or whatever, 0.4, 0.6 or 1.6, right? So by taking off a solar mass and making it into a 1, once it's sort of settled down again, it looks pretty much the same. The sneaky way of doing it is in daylight how we discovered this, and it works, but not often enough. Well, it wasn't often enough. Is to get rid of a red giant, you don't get rid of the envelope, you get rid of the core. You give the core a jerk, a jolt. So as my black hole now, this is a black hole, 10 solar mass black hole, gets close enough to the core, flies by, it accelerates the core, gives it a zip flying up here. You can see it's moved a bit, and there's a shockwave propagating down. And if I give this a big enough jolt, then I can take away the core with sufficiently little mass. It looks like a funny bright blue thing rather than a red giant. But I need a massive object, I need to get close. This is rare. Okay, if I'm allowed to do this and just dial up all those stellar mass black holes, I can make this work. I could show a nice surface plot that looks like the original ones we saw a few years ago. But the total mass of stellar mass black holes would exceed the mass enclosed in the inner point few parsecs by a lot. So this does not work. Or at least it didn't work if I was trying to exclude everything out to 0.4 parsecs. But this will happen, and it will happen more often in the middle, and it may be now that in combination of a number of things may indeed get rid of the giants that you do see missing in the inner 0.1 parsecs or so. Okay, key idea number 3 then is production of exotica. Okay, I'm going to talk about 2 things very, very briefly. We've heard about all of this already, pulling things together, but I'm going to make 2 comments. So I'm going to talk about the S stars briefly and about GN. Okay, these G1 and 2 and others potentially. And I'd say here rather blandly, tell us something about processes, but I'll tell you what I mean by that. So the first comment is about the S star. So to remind everyone, we all heard about the Hills mechanism. It's actually interesting historically because this is actually an unusual example of a genuine theoretical prediction, right? Before observations, right? Jack Hills understood this would happen, and it's actually historically, I think, true, others should comment, that for a while it was a big concern that we didn't see the hypervelocity stars. It was potentially evidence of an absence of a supermassive black hole. So the idea is a binary comes down, the binary gets tidally disrupted, one thing is superbound and one thing is super unbound, and that gives you a hypervelocity star. My question is the following: can one kick a snowball? What the hell does that mean? More, can you score a penalty goal with kicking a snowball is what I really mean. What that means If this binary is a super soft binary, I don't mean a super soft binary, but I mean a really soft binary. Question, can I still scatter it into the galactic center without breaking it up? So imagine it's scattered in by prosaic two-body scattering. Now I do remember, I read the books, there's a Coulomb logarithm. Most of the scattering that matters is the accumulation of small scatterings further out. But nonetheless, there are some smaller number of events closer by. And if I had a really close encounter between my soft binary and another star, it would break it up. So a genuine question, which I don't know the answer to, is if I'm only allowed two-body scattering, to what extent does that exclude soft binaries coming in towards the galactic center? This in turn affects what kinds of things can be hypervelocited and what kind of things can be S-starred, right? However, it may be that this really excludes that, and then you conclude the things we already knew maybe, that you have all these other mechanisms to increase the eccentricity. So resonant relaxation and other things, cosi, I guess not so much cosi, but resonant relaxation potentially bringing you in. Right, Gn, okay, G1 and G2, just going to very quickly throw in for my lot what I think you all remember. This guy went through the red giant, picked up some mass. Potentially, if that's a white dwarf, and we'll see in a minute, there's lots of white dwarf red giant collisions that do this. Potentially, could this object be your G1, G2? So a white dwarf going through a red giant will absolutely hit it. I think I can tell you how much mass it grabbed reasonably. It's between 10 to the minus 2, 10 to the minus 3 around solar masses. I have no clue whatsoever beyond that what this does next. Because again, we do what we do with codes. Codes are good for answering particular questions. And the SPH method used here, and the way we used it, is pretty good at figuring out how much mass I grab initially. But I'm not doing anything with cooling. I'm not doing anything with radiative transport here. So I have currently no idea what this object would look like. But I can tell you when these objects are made and how often. So potentially, these objects could be an interesting contributant to the GNs. So how often do I hit and when do I hit? Very quick. So this plot here, we'll just focus on this one down here for a second. Bottom left, this is what I call the zigzag plot, if you can imagine why. Log of stellar radius versus accumulated chance of having a collision. So you're a one solar mass star, and you're going to evolve all the way through it to a white dwarf. Question, when does our chair get hit? Okay, does he get hit on the main sequence, which is long-lived but small? Does he get hit on the giant branch, when he's a bit bigger but a bit less lived? Or does he get hit at the very tip of the AGB where he's super big but short-lived? Answer depends on your V infinity. Because thinking back at the cross-section, if V infinity is low, if I'm in the GC regime, I'm super focused. If you remember the equation, cross-section goes as radius. If I'm super not focused, cross-section goes as r squared only, right? And if you think about it, r squaredness promotes giantness, right? Yeah, being bigger is a bigger win for him when the cross-section goes as r squared, not as r. And that's what we see in this diagram. This is the accumulated chance of hitting, normalized to 1. For the globular cluster regime, it's all main sequence, main sequence, main sequence. First giant branch, so like 20% of encounters on the first giant branch, 10% or so on horizontal branch, tiny, tiny fraction on AGB. If I'm in the gravitationally non-focused, the O dot regime, the super O dot regime, where this goes as r squared, then you see it's all giant branch, a little bit of horizontal branch, but now suddenly the AGB becomes important. Because again, bigness matters more because cross-section goes as r squared, not r. This is for different masses. You can read about it when I finally write about it. We'll tell you more over lunch. But this changes as a function of mass. This is only a 3 solar mass star, and suddenly the horizontal branch is super important. So evolutionary differences between a 1, 2, and a 3 matter when you're thinking about what's hitting them, and this is important for us to think about. Okay, very quickly, just because we've done something. These are collisions in a simulation between white dwarfs and red giants. And this is a particular mass. This is a whole load of masses here. But just to focus on this one for a second, it's around 1.4, 1.5 solar masses. And these are all collisions that happened in our simulation. I can explain all the details if you're interested later. But the point is the following. You want to see lots of dots up here, lots of dots up here, some dots here. This is going up the first giant branch up here, right? Then you're on the horizontal branch, and then the AGB. And you can see, because we're not very focused, lots of our collisions happen when we're quite big. Yeah? Yeah. Okay. Idea number 4 then, depletion engine. The point here is that the galactic center is good at making exotica, but it's also potentially good at getting rid of things, right? And this is also telling us about what's going on. Again, I'm not going to go through all of these, but these are various ways you could think about to get rid of a red giant. We've talked about some of these already. So for example, hitting a red giant, but you could also hit main sequence stars. If a few years ago, if we didn't know about when the depletion kicks in at all, we might say, okay, main sequence stars can get walloped by white dwarfs, black holes, neutron stars. You hit a main sequence star with a black hole at V infinities that are large, you break the thing up, or you grab a bit of mass, you super accrete, right? You don't have a main sequence star afterwards, but then you would have no giants at all. And we all remember what Reiner told us yesterday. He does have giants. If he goes faint enough, going up the giant branch off the main sequence, he sees them. They're where we should be. He's got a nice cusp. So we know now something better than we knew before. This isn't doing it for us. We're not getting rid of them before the giant branch. We're getting rid of them later. Sorry? But only later, right? So he doesn't have, no, because his black line doesn't have a hole. If you remember his plot, okay, and the black line was the fainter giants, right? Okay? Yeah? He's nodding, so I've got it right. Okay. No, but everything, okay, but that's accumulated light. But the point is that's all the things going up the giant branch. Right? When you look at my plot here, it's all this stuff here, basically, right? Can we come here, right? So we're not getting rid of them halfway on the main sequence. That's the point. Okay, I think that's what it's telling us, right? There's various other ways, and this got mentioned too. You can dynamically do things. I'm not going to go through all this now, but you could potentially just move the objects out. We heard already about mass segregation earlier in the week, for example. Okay, but I want to make one important point before I finish with 5. I'm almost done. This is important. This is the most important thing I've said so far. Okay. This plot is a plot of K magnitude versus time for a 1 solar mass solar metallicity star. Now let's imagine, so what you're seeing here, this is observations, is lots of these things here, often called the red clumps. We call them the horizontal branch. They're core helium burning, right? That's this phase here, right? Now a tricky to answer question, but very important one is the following. Which giants don't have the cusp, right? Remember, we saw that stuff further down here maybe had a cusp, but at some point, some of them are missing a cusp. Now let's imagine the following is true. Let's imagine that the only things missing in the cusp, because they've been walloped, something has done them in, okay? If it's only the top guys here, literally only these are missing, and there's so few of these anyway. So let's see, all the bright things we're seeing are essentially here. They're here. If it's only those that have been walloped, the walloping thing might have only been on for a few million years. Yeah? Because they're only a few million years old. This is a few million years right here. You can't possibly read it. This is 100 million years. So something that's happened only in the last 10 million years could have walloped all of those bright giants. But if the horizontal branch here is also depleted, then it means, and it's significantly, then it means it's been on for the entire length of the horizontal branch lifetime, which is 100 million years. This is interesting because imagine you decide that that is the case, then the thing that wallops them has to have been on for 100 million years. So if you think it's a disk and stripping, then that disk has to have been around 100 million years, which is very interesting. That was the important point. Great. I'm only going to make this comment here. Good answers always find good questions in the end. Okay? We were trying to get rid of this, a paper some time ago, probably a very long time ago to some of you, where we were trying to get rid of the giants by throwing in a binary. Okay? So binaries encountering the red giant are good at getting red giants because you have basically a binary single encounter where a single star is the core of the giant within the envelope. This is an example of a simulation. It was published then. And the interesting thing here, we were trying to get rid of the giants, and it sort of works. It's like all the other things. They sort of worked, but not often enough. But now let's turn the question on its head. Let's forget the giant. The giant is merely being used. It's a tool. The thing I care about now is the binary. Let's imagine this is a useless binary. My definition of useless is a compact binary that will not merge in a Hubble time. So I have a black hole and a neutron star, separation, say, 30 solar radii, say, given the mass, would have merged in a Hubble time if it was 20 solar radii. By doing work on this envelope, or doing work kicking out the core, it's kicked out the core, that's how it's captured. It's called a plant in snooker. By doing work on that envelope, I can take a useless binary and make it useful. That's the point. Either by grinding it down, or also equally importantly, right, taking away some angular momentum, making it eccentric. Shorten the merger time. Okay, so that was making usefulness of useless binaries. Very last idea, Discworld. Doug told us a lot about this already, but I think this is very important. So the first point is the following, is that if we see about one young disk of stars, but if I'm allowed to make one every 100 million years, this has been mentioned by others this week, the number of stars I make, my stack of disks, is comparable to the total stellar mass. So it's significant, right? We know that nuclear stellar clusters can be made, I think, by globular clusters sinking in. So I think you could well have both happening roughly equally likely, both contributing. It could be that the disks are only making massive stars, essentially, for example. There's a very important point here. Even if I only make half the stars this way, I actually increase the number of stellar mass black holes by a factor of 10 if I follow what we see in the current disk. You see that? So in other words, if I'm allowed to do this, half of the stars, I double the number of neutron stars, but increase the stellar mass black hole number by about a factor of 10. So I can increase the number of stellar mass black holes enormously. Penultimate slide here, I'm about to summarize. Okay, but how you make this thing is uncertain. This is just pointed to put people who have done work on this, including I'm on this paper. Basically, you could throw in a GMC, shred the cluster, make a disk around the black hole. But I think there's, and in general, people are looking at that, but I think it also emerged, well, Doug talked about it earlier this week, is you could also potentially use the disk itself to grow the low mass stars. So forget about star formation itself. Imagine you've got low mass stars, you make a disk, right? I'm a low mass star that happens to be in the disk. He's a low mass star but highly inclined from the disk. I'm the one gaining the mass. So some small fraction of the stars, about 1%, depending on your thickness of your disk, are in the right place or the wrong place at the right time, depending on your view. And if you have a beefy disk, then you can do this, right? Maybe. This is an example of stripping of the stars. So not only do we gain massive stars by gaining mass onto the main sequence stars, that same disk is a potential object to strip the giants, right? So remember again, it comes back to this plot again, very quick. As I'm going up the giant branch here, I'm getting brighter because I'm getting bigger. A bigger envelope is a fluffier envelope. So those fluffier envelopes can be stripped as they slam through the disk. Main sequence stars have a much higher column. They don't get stripped, even for your aforementioned disk. Okay. So what you can do then with one disk is you get two things. You can potentially grow the massive stars if you're dense enough. And at the same time, you can strip the giants. So stripping the giants turns out to be almost like mass transfer in a binary, because you go around every 10,000 years, taking off a small fraction of the envelope. And you can actually follow it like binary evolution, like a star losing mass slowly in a binary. And that's the calculation we did here. And all I want you to take away from this is for a reasonable disk, a less umphy disk, then you can get rid of some of them. But it may well be that when you make this disk more umphy, also helped by Pao and his colleagues who pointed out that your disk may be lumpy, that helps. This may be a way of doing it. So you may get two things for the price of one. But then again, if the horizontal branch is depleted, this disk needs to be on for 100 million years. Let me conclude. Okay, so just again, very quickly, chicken and egg, what's made first, supermassive black hole or nuclear stellar cluster? We saw this functionality of it, the fact that speed matters. In my GC clusters, my clusters without supermassive black holes, lower speeds meant lots of things could happen. When I go to O dot, my speeds increase and other things can't happen, changes what happens. We saw that exotica can be produced, the S stars and other things. We saw the depletion of objects like red giants potentially. And finally, we ended by pointing out the potential importance of either one or many disks over the history of the Milky Way. And on that, I'll close. Thank you.